All right, here we go. Let's talk about angular momentum. So if you remember what linear momentum was, right? It's a little off to the side here. P was equal to mv. The direction of the momentum vector was equal to mass times the velocity vector. So therefore the direction of the momentum vector was always the same as the direction of the linear momentum. So this must be of the center of mass, and that is super important because that's what we've been assuming all along. Now, angular momentum. Well, what is linear momentum? Linear momentum was a quantitative measure of how hard it was to stop an object that was moving. And so angular momentum must just be a quantitative measure of how hard it is to stop an object from rotating. So if we were to take then a guess, a stab at what that equation looks like, well, first off, symbol for angular momentum, capital L, and it's going to be a vector. What do you think it's going to equal? Well, over this entire journey that we've done with rotation, we've seen that our rotational quantities in a lot of ways mirror what our translational quantities look like. For example, we had kinetic energy translationally was 1/2 mv squared, and kinetic energy rotationally was 1/2 I omega squared, where angular velocity took place of the linear velocity, and angular inertia or moment of inertia took place of the mass, which is linear inertia. So if in that perspective, if P is equal to mv, then L should equal to, and if you said to yourself I omega, you're right. Remember, omega is a vector. So that means whatever the direction of the omega vector is the direction of the angular momentum vector. Remember, we curl our right hand in the direction of the rotation, and our thumb points in the direction of the omega vector, and that's the same direction as my angular momentum vector. So here you go. This is going to be the way of calculating this for a rigid rotating object. Okay, so that's pretty straightforward there, although not all that interesting. What makes this all interesting is, remember when we studied momentum, we weren't really interested in momentum per se, we were interested in the conservation of linear momentum, right? So let's remind ourselves of that, conservation of linear momentum. And what did that law say? That law said, in the absence of net external forces, linear momentum was conserved, right? Or in terms of our symbolic way of saying that, if the net external force was equal to 0, therefore the initial momentum of the system was equal to the final momentum of the system. Very simple in terms of that conservation of linear momentum. So we said that linear momentum was conserved for free or unconstrained objects, right? That's oftentimes what this came down to. Were our objects free / unconstrained? So I crash into a wall, no, linear momentum is not conserved because the wall is constrained. But if I crash into another person, or if one cart that's rolling along crashes into another cart, or one pool ball crashes into another pool ball, all those things are not really constrained, so linear momentum was conserved. So now if I want to talk about the conservation of angular momentum, the condition is not the same, but you could probably guess at the condition. If linear momentum is in the absence of net external forces, linear momentum is conserved. And if angular momentum is just taking the translation of the translational terms to the angular, I think you can take a guess then that this must be in the absence of net external, and if you guess the word torques, you're right. angular momentum is conserved. Okay, and that's going to say if sigma tau external is equal to 0, therefore L initial for this system is equal to L final for this system, right? Now, just because net external torques are equal to 0 doesn't mean net external forces are equal to 0 or vice versa. These are independent conditions, and so part of this is going to be about identifying when one of the conditions is met or the other condition is met, so that we know what's conserved in each situation. And while we're talking about conservation, let's bring in the other conservation law we know, which is, of course, the conservation of mechanical energy. That has a totally different condition. That's in the absence of work non-conservative. These two conditions don't care about whether the force is conservative or non-conservative. This only cares about whether the force is external or internal to the system, meaning between the members of the pairs or not. And this is about torques. So you can have forces that don't cause torques. And then even if you have forces and they cause torques, if they're internal to the system, it doesn't violate this condition. So there's several layers of that, right? So I can conserve energy without conserving these. I can conserve angular momentum without conserving linear or energy. And so all the conditions are different. That's really what my point is. And it's about asking about those conditions in each situation to know how to go about these problems. But let's go to a very simple angular momentum problem. And this is physically what I would have done. I would have taken a stool, right? So here's a stool. And I would have sat on the stool, but first I would have put my rotating platform, that green rotating platform, on that stool, and I would sit on that stool. So here I am sitting on that stool. And I would hold in my hands 2 weights. We actually did this early in the year. It's so weird looking, but there it is. So this thing would be rotating. We're looking face forward. So this would be going around like this or around like this, right, up to the ceiling. And we actually saw what would happen, because what I would do here is I would pull my arms inward, right, so that now the masses were closer into my body. Apparently my arms just shrunk. But there you go, and that's the demo that I would have done. What would have happened here? So this object, let's say, was rotating like this. I'm not pretending I'm an angel, ha ha ha. So that's my omega initial. And then what happens here? And if you remember, this is the same thing as what happens with an ice skater. We know when an ice skater pulls their hands in closer to the body, they spin faster. Well, why? Well, here, let's look. L initial of the system is equal to L final of the system, and because the net external torque is equal to 0. So let's examine that. What force here would be causing a torque? Well, notice I pull to go from here to here. What I'm doing is I'm exerting a force inwards along my arms to pull the masses inwards. Where's the rotational axis? Well, the rotational axis is here. So even though there are forces acting, those forces don't cause a torque because they act through the axis of rotation. So I meet my condition not because the torques are internal or external. I didn't even get up to that question. It's because the torque doesn't exist because the force acts through the lever on distance. So there you go. I've met my condition. Angular momentum is conserved. So then how does that display itself? Well, I've got I initial omega initial is equal to I final omega final. Well, what did I do in this process? Well, from beginning to end, I think if we just understand I as, that's just the sum of the MR squareds. The sum of the MR squareds, essentially. Or the further it is that the mass is from the axis of rotation, the greater that the moment of inertia is. Obviously, we have better ways of calculating than MR squared based on the shapes of these objects, but just as a conceptual idea here. So I think it's pretty obvious here then that I initial is bigger than I final, right? Because I pulled my arms in. Therefore, omega final is greater than omega initial. And that's why you spin faster when you pull your hands in, and you would spin slower when you put your arms out. And so anytime you have an object that's rotating that changes shape, based on how that shape changes, so does the rate of rotation. Some other examples that you might think about this is shaping clay on a potter's wheel. That could affect the rate of rotation of the potter's wheel. Obviously, divers are another really great example of this. You know, they have their tuck positions, they have their pike positions. Gymnasts do the same thing. By changing the shape of their body, they're able to show their changes in rotation. I'm going to put a video together of a bunch of examples of this just so that you can see this in action. And so that's the basics of the concept of conservation of angular momentum.